Welcome to lecture number 10 on adaptive signal processing. In this video, we are going to discuss gradient descent algorithm. In particular, I'll be giving you an introduction to this topic, and also I'll provide you one 1D example with simulation result from MATLAB. Gradient descent algorithm is an optimization algorithm. It finds the minimum value of a cost function. It is very simple and easy to implement. Though it is an old algorithm, still it finds several applications in practice, like in machine learning. You know, machine learning is a hot topic. So we'll be discussing few problems from machine learning to discuss gradient descent algorithm. So in this video, you will find a detailed discussion on gradient descent algorithm. We'll provide many examples. We'll show all the analysis step by step, and those are shown by MATLAB simulation results. Particularly, I'll deliver a series of lectures in this topic. So first topic is gradient descent algorithm. Next, we'll discuss Newton's algorithm. Then stochastic gradient descent algorithm, conjugate gradient descent algorithm, and other related algorithms. You see, all these algorithms are gradient-based optimization algorithms. So we'll discuss one by one, and I hope it will be interesting to understand those variants of gradient descent algorithm. Now, we'll start gradient descent algorithm. So this optimization technique is used in many fields, like in machine learning. In machine learning, deep neural networks support vector machine, logistic regression. These are few topics in machine learning. Their gradient descent algorithm will be useful either to train the neural network or to find the parameters of support vector machines or logistic regression parameters. So we'll be discussing few examples from machine learnings. In adaptive filtering, you see there are several applications. One is unknown system identification, channel estimation, designing equalizer. So those things we have discussed in our course. So everywhere this gradient descent algorithm concept will be useful. So from this gradient descent algorithm, we'll find some adaptive algorithms for particular applications. So in this context, I just like to compare between machine learning and adaptive filtering. In machine learning, you will see that there are huge number of raw and labeled or unlabeled offline data required. These are the requirement, because machine learning algorithm will accept a huge number of such data, then only it can train the higher level of neural networks. Whereas in adaptive filtering, you will find that there are limited number of online input-output data. So depending on very limited number of pilot sequences, those data are called pilot sequences. So using those pilot sequences, we need to train adaptive algorithms or adaptive architectures. So this is the difference. But remember, both the things, machine learning and adaptive filtering, they are basically learning process. So in machine learning, you will find huge computational complexity due to deep neural network, whereas in adaptive filtering, the complexity should be as low as possible because it is used for online application. So machine learning, they are mostly suitable for offline applications, though there are recent people are working on machine learning so that those architectures will be also applicable for online applications. But most of the algorithms or architectures for machine learning are for offline. But adaptive filtering, all the algorithms, adaptive filter algorithms, are specially designed for only online applications. Okay, because it is considered that system parameter can change over time, and adaptive algorithm will be able to track those changes. So this is the main difference between machine learning and adaptive filtering. But again, I'll repeat that both the algorithms are learning algorithms. And you'll find that there are lots of similarities in their architectures. So if you have a good understanding in adaptive filtering, you will find very easy to understand machine learning algorithms. And I'll be discussing one course, that is signal processing for machine learning, in future. There you will see that there is a close relation between adaptive filtering and machine learning. Okay. Now, first I'll start with the adaptive system identification problem, because in this course we have introduced that concept, and from that we'll try to get motivation for this optimization technique, gradient descent algorithm. So let us see. So you see, this one is your unknown system coefficient W oft, and this is your additive noise Vn. So Xn is the input to this unknown system, and Dn is the output of this unknown system. And our objective is, using these two, Dn and Xn, we need to train one filter coefficient W, so that this filter coefficient W will be very close to W oft. Okay, means it will try to estimate the parameter of unknown system coefficient W oft. So in other words, if the output of this filter Wn is Yn, then Dn and Yn will be close, so En will be minimized. Okay, so here En is this Dn minus Yn, the gap between Dn and Yn is the output of this filter, and this filter I have considered FIR filter with length L. We'll assume that unknown system is having L coefficients, capital L number of coefficients. So here this output Yn easily we can rewrite as in this form: W transpose n Xn vector, where Xn vector is our input regressor vector that we have discussed in my previous lectures. So it will contain the first L samples, input samples, starting from Xn, current sample, Xn, x of n minus 1, x of n minus 2, up to x of n minus L plus 1. So this is our error. So we'll choose our cost function as expected value of E square n. So you see this expectation is over ensemble, it's ensemble average. Okay, and we'll try to find the minimum cost, and for that we need to find out the solution for W. So in that case W should be independent of n, not required for n. Okay, so here if you simplify this one, if you replace this en that we have already discussed, then this cost function reduces to expected value of d square n minus 2 times W transpose n. So you can remove this small n index here, W transpose P plus W transpose R W, where P is cost correlation vector between Dn and Xn, and R is the autocorrelation matrix of input sequence Xn. Okay, and you see this input sequence is stationary process. Okay, so thus this R is independent of small n and P is also independent. It's stationary. Now in this case, this Xn and Dn, Xn is input sequence and Dn is the output sequence. So this pair is called data. So this data is available with the help of this data. So it is also supervised learning. It's a level data, that kind of thing. So pilot sequence. Okay, so then these sequences are given, and with the help of these sequences we need to find the optimum solution. So this is the cost function that we have considered. The optimum solution, winner solution, is given by simply W star equals to R inverse P. That also we have discussed in my previous lectures. So you can go through those previous lectures. But here you see, so this is one short solution. We can find the optimum solution, the best solution, the mean square in the sense of mean square error. However, here you see there is a difficulty to find R inverse when the system length is very large. So if the system length capital L is very large, suppose if you consider 1000, so R matrix is of dimension 1000 cross 1000, and for such big matrix it's very difficult to compute its inverse. It's not easy. Okay, so we'll try to avoid to find the inverse of this matrix capital R. That is one objective. And again, this equation, this one shot equation, is also not suitable for online application. We want some gradual update, iterative algorithms for adaptive algorithms. So what we want one iterative algorithm which will give you this optimum solutions W star, that is equals to R inverse P. So this is the cost function. So this J equals to expected value of d square n minus twice W transpose P plus W transpose R W. Okay, and it's analytic function. And also we assume that it is a convex function, and its optimum solution will exist. And its solution is given by R inverse P. It's a one step solution, but we are looking for one iterative solution which will look like this one, that from my previous step Wn, I'll add one correction term, we'll get a new weight Wn plus 1, and we are assuming that we are expecting that this Wn plus 1 will be closer to our optimum solutions. So indeed, at infinity at least, W infinity, it will be exactly equals to W star. So there is no gap. Okay, so in that case it will be called unbiased estimator. Exactly you will get these things. Okay, so for this we'll use gradient descent algorithm to get those correction term. Okay, so this here is the motivation why we are going for gradient descent algorithm. So you want to get one iterative algorithm for this optimum solutions R inverse P. We want to avoid this inverse of R matrix, yet we want to get same optimum solution W star using iterative approach. Okay. And we will also consider two problems from machine learning. First problem will be the 2D regression problem that will be discussed in detail, and the perceptron training, okay, the training algorithm for perceptron. So these two will be considered in detail in next videos. Okay, so you'll be watching those videos, you will find these two applications. So now first we will discuss the concept of gradient descent algorithm. We'll try to get this algorithm through some logical discussion. So first I'll take one example. With the example, we'll try to understand what is the meaning of gradient descent algorithm. So we'll consider first one analytic function, and suppose this cost function is like this, is j omega. It's a one-dimensional problem. It's only w only, or you can write w. J of w is 4w squared minus 12w plus 13. Okay, so only one weight w. So this one we want to minimize. So objective is to find w star, that is argument minimum of this j of w for this w. Okay, so which w will give you the minimum value of this cost, that is called w star. Now for that we can use our general approach, and general approach is this, that first we will take derivative of this cost function with respect to w, this variable, and we'll equate this derivative to 0, then we'll solve it. Okay, and that solution, obviously one of the solution will be w star. Okay, so w star, this optimum one, at that point the derivative should be 0. So that is the meaning of the first equation. And second one, the second order derivative at that point w equal to w star, it should be positive. Then only we'll get minimum value of this cost function. Okay, and if it is opposite, if it is negative, less than 0, then you will find that at that point you will get maximum value. Okay, so gradient descent algorithm is used to find minimum value of a cost function, but there is another version, gradient ascent algorithm, which could be used to find the maximum value of a cost function. In that case, we'll check this one, second order derivative should be less than 0. Okay, so this is the standard approach to find and minimum point of a cost function. If minimum, okay. Now, for this problem, if you take derivative of this cost function j, you'll see the derivative of w squared will be 2w, so it will become 2 into 4 is 8, so 8w, and derivative of w is 1, so here it will be minus 12 only, and derivative of this constant is becoming 0, so that I have not written here. So derivative of this cost function is simply 8w minus 12. So w star, so one solution w star, and this derivative will become 0, that will use. So 8w star minus 12, it should be 0. So w star should be 12 by 8, means 4 by, this is 3 by 2, that means 1 by 1.5. Okay, so this is a solution. That solution easily we can find out analytically, right? And we can also check the second order derivative, and this second order derivative, you will see, if I take derivative with this one again, then we'll find second order, and derivative of this one, w is 1, so it is only 8, and this derivative is 0. So you see the second order derivative is always 8, that is positive, meaning is that this cost function will have only one minima. Okay, and that minima is 1.5. So there is no maxima, nothing is there. Okay, so because it is, the second order derivative is always positive, it cannot be negative, so it can't have a maxima. It's growing. Okay, it will have infinite magnitude to certain values, right? Now for this problem, I have plotted this cost function g of w versus w, and this plot, you see, this is a convex function. It's a quadratic equation, and I have considered this one from MATLAB plot. I'll discuss this code from where we have got this thing, and we'll discuss in detail the MATLAB code for this gradient descent algorithm. Okay, and you see, this is the minimum point here, w star equal to 1.5. Okay, and this problem we can also solve in this way, very simply way. So we can rewrite this cost function as this 4w squared, you can write 2w whole square. Then we can break this thing as 2 of w as 2 into 2w multiplied by 3. And this 13 you can rewrite as 3 squared plus 4, 9 plus 4. In that case, this first 3 will give you 2w minus 3, that whole square, and plus 4. And you see, this equation, this term will be always positive because it's square value. So if it is always positive, its minimum value will be 4 when this value is 0. Okay, so this cost function will attain the minimum value 4 when this 2w minus 3 equals to 0. Thus, you see, 2w star minus 3 equal to 0, so w star equal to 1.5. So in a very simple way, we can solve this problem. However, this kind of approach is not suitable for higher order cost function because analytically also we can't, it's not feasible. So if it is order is more, fifth order, sixth order, like that, it is very difficult to rearrange in this form, square form. So better we can go for general approach. So from the first equation, you'll see we'll find the maxima or minima point, the optimal point, because just solving this first equation, dj dw, that I'll put it 0, and if we solve it, we'll get some solution for w. Those w could be either maxima or minima. And from second one, we can check whether it is really minima or not. Okay, and it will be minima if second order is positive at that point, w equal to w star. So we'll investigate these two equations in greater detail, and from there, that point of view, we'll try to get gradient descent algorithm concept. Now, let us start with this general approach. So these two steps. Now I'll consider first one cost function, a general cost function, not only the quadratic equation. Okay. Now you see this function, it looks like this. It is having one maxima here, one maxima here, and one minima here. Okay. So if I plot the derivative with respect to this w, so obviously you see whenever there is a maxima, its derivative is 0 because its slope is becoming 0. Obviously at that point its value will be 0. Right? Similarly, at the minima also this slope is becoming 0, so this derivative is 0. And here also slope is 0, its derivative is 0. Okay. Now you see at this stage, this function j is increasing and then it will attain a maximum value. Okay. So you see derivative value is gradually reducing and is becoming 0, but as it is increasing function, so derivative value is positive. So from positive point, it is now decreasing, it is becoming 0. Okay, and afterwards, so as we are moving to right side of this w, of this maximum point, this function value is reducing, means gradient is negative. So between these 2 points, every time gradient will remain negative. Okay, so from here it will start, again it will become 0, and in between it will remain negative. So somewhere it will have a maxima, negative minima, and then again it will come to 0. It has to be. Okay, and similarly here, from this minima to maxima, the function is increasing, mean slope is always positive. So it will remain positive somehow. But again, it will start from 0 here, and again it will come to 0 here. So somehow it should get this kind of shape. Okay, and later, so it will be like this. So it is decreasing function, means slope is negative, and it is, if it is becoming constant here, so its slope will become 0 here, right? I hope you have understood this figure, the derivative function of this cost function j. So that we have drawn separately. Now we'll also draw the second order derivative. So from this first order, if I take again derivative, we'll get second order. So again similarly, so if I consider the first order derivative there, in this function here it is a minima, so its slope is 0. So second order derivative should be 0. Similarly, here it is a maxima, its derivative is 0, so here it is 0. Remember, the second order derivative is basically derivative of first order derivative. Okay, so now between these 2 points, again remember that I discussed, so this is minima and next one is maxima, function is increasing, so here slope is positive, so here you should get a positive value always between these two, so you should get this kind of shape, right? Now left side, this function is reducing, so it is something negative, so this side you should get some negative value. Similarly here also, from maxima it is reducing, so here also you should get some negative value. Okay, so that I can put here. Now if you look at this point, if this is maxima, that time derivative is 0, the second order derivative will become negative. Okay, and if it is minima, derivative is 0, but second order derivative should be positive. Okay, and if it is maxima, again you'll see this second order derivative is negative and derivative is simply 0. So that is obvious. Whenever you will get a minima value, that means from the left side function should decrease, means the gradient should have a negative value, and right side function should increase, gradient should have, or derivative should have positive value. So at this point, the first order derivative, left side is negative, right side is becoming positive, and it is passing through 0. That means at this point the slope should be positive. Okay, the slope of this first order derivative should be positive, that means second order derivative should be positive. That is the idea. Okay, right. But here we will focus on this part only this minimization part, the how when function is reducing and it will attain and minima level. So that part only will focus in detail. We'll discuss in detail. So we'll consider one quadratic convex cost function, and we'll go for minimization problem. So this is my quadratic cost function, first order. What is, and this is it's only single variable w, and its derivative, you see, if it is a quadratic function, then derivative will become a straight line. Okay, and you see, if w star is the minima point, the right side is increasing function, means positive slope, and left side it's a negative slope, but slope will remain same throughout. Okay, so it is passing through this origin, this one. So at w star, derivative value will become 0, right side is growing, left side is negative, right? So if I consider one point w1, you look at, that is left side of, in the left side of this optimal point w star. Okay, we are here. So that time this is the cost and this is your derivative, so we'll show that one. So this is the cost value and here is the derivative value. So you see, at w1 derivative is negative, so derivative at w equal w1 is negative. It implies that function is reducing. Okay, now if I want to move towards this optimal point, obviously we have to move from w1 to right side, okay, through this arrow. Okay, so from w1 we need to add some positive value. some positive increments should be added with W1, then we can come close to W star. Okay, because our objective is from to move from W1 towards W star. Okay, so this kind of increment we can add, and then if we add, we can come up to this point W1 prime. Okay, so W1 prime will be closer to W star compared to W1. Okay, similarly, if I consider one point W2, which is on the right side of this W stars, in that case, you see this derivative value is positive, imply that at this point function is increasing. So in that case, we should move to the left side of W2 in this arrow, then only we can come closer to W star. Okay, so from with W2, we'll add some negative increment. Some negative value should be added with W2, means we want to reduce the W2 value. Then only we can come closer to W star. Okay, and if we do so, then W2 prime here, that will be closer to W star. So from this discussion, you see one thing, the sign of this increment. So when the derivative is negative in one point W1, when derivative was negative, the increment was positive. And W2, when derivative is positive, increment should be negative. Okay, so from this we can conclude that the sign of increment should be opposite of sign of derivative. That is confirmed. And this is very obvious, because when derivative is positive, like this one here, that time function value is increasing. So we need to reduce the value, because function value is increasing toward the right side of this W2. So we should move on the left side of W2. And when the derivative is negative, that means the function is reducing to right side. So we can continue to right side. Okay, that means whenever derivative is negative, we should add some positive value. Means opposite of that gradient value should be added, right? So sign of increment should be opposite of sign of derivative. That is confirmed. That's the first conclusion. So in a iterative algorithm, if we consider this kind of algorithm, the Wn plus 1 should be Wn plus some correction term. Then in the correction term, the sign of the correction term should be the opposite sign of the derivative at Wn, right, at that point, right? Now, what should be the magnitude of this correction term, right? Now you see one point, if we are here W1, in that case the gradient is negative, but the magnitude is large. Okay, and if you compare with W1 prime, you see its gradient value is small. So when gradient value is large, it signifies that it is far away from the optimum point. Positive and negative, that meaning already have discussed, but magnitude wise I am telling you that if gradient value or derivative value, so here one thing, the derivative of a function, first order kind of thing, quadratic function, that slope I'll call also also the gradient, but we will define the gradient concept for second order, so or higher order polynomials. Okay, higher dimensional rather problems. That time we will define the gradient. Truly, what is the meaning of gradient? So here the derivative and gradient is same meaning. Okay, so now what we are discussing, that if derivative value is more, that implies that it is far away from the optimal point. So we should take a longer step to reach closer to W star. And whenever the derivative value is small, then we can guess that we are close to W star, so we can take less step. Okay, so you see, when we are far away, that time gradient value is large, we need to take larger step. And when we are closer to W star, gradient value is also small, we need to take small steps. So it looks like that if we take the magnitude of this correction term directly proportional to the gradient magnitude of this gradient, then we are done. Okay, at least we can make proportional to these things. We can take square of this one, we can take cube, it may work, you can check, but simple proportional thing will work nicely. Okay, so what we will do, so we'll consider the magnitude of this correction term is directly proportional to the magnitude of this derivative term. Okay, so here we have considered sign, here we have considered magnitude. So if you combine these two together, then we can say that this correction term is directly proportional to negative of gradient. Negative is coming from the sign, okay, and this is the magnitude. So that is the basic concept of gradient descent algorithm. So correction terms should be made proportional to negative of the slope at that moment. Okay. So this is the idea. In that case, we can introduce this correction term. We can write as mu times of this one. Mu here, we can introduce one learning rate. So in machine learning, mu is called learning rate. And in adaptive signal processing, generally we will call it step size. Okay, so this terminology is different for different researchers. Because someone considered this correction term at the step, learning step. They are calling it learning step total. Okay, so but here in this lecture we will consider that mu is only learning rate or step size, and this is total step. Fine. Okay, correction term is a total step. Okay. So here you can see one thing. So if we consider a larger mu, means larger step size, then we can expect that it will converge fast. You can get faster convergence. And if we reduce the mu value, then we may get slower convergence. However, this is not always true. We cannot make mu infinity. If we make mu too large, then it may affect. The algorithm may diverge. Okay, there should be some upper bound on mu. So we'll consider all those things. So then question is, what is the optimum value of this mu? The fastest convergence. So those things will be discussed later. Okay, we'll go for this one optimum mu, while we'll discuss for higher dimensional cost function. Now I'll give you one MATLAB code. I'll show you all the analysis step by step. So here you will see one cost function, the j. I have considered the same cost function, j equal to 4w squared minus 12w plus 13, right? So this code is very simple. I have written so many lines because I want to show you all the steps to the MATLAB only. So to get all the plots, all the analysis from the code only, I have written all the lines. But basically this is the cost function here. No need to write other things. Just you can specify your step size. Here I have considered mu. Mu is the step size 0.2, and we should specify our initial value of Wn. Okay, this thing you can skip. No need to write anything, right? And then we should use one for loop, and that for loop, and it is I equal to 1 to iterations. First we need to compute the derivative value, the gradient value. Okay, so in this case gradient already you have shown that it's 8w minus 12, so 8wn and 12. Okay, and we want iterative equations, that is equal wn equals to wn minus mu into g, and g is your gradient. And you can skip the steps, and this is the end. Okay, this is very simple algorithm. If you want this full code, then you can write an email to me. Okay, I'll give you this one. I'll provide you the code. Okay, so my email ID, you can note down. It would be this one, rajiv.das.iit@gmail.com. Okay, right. Now, so this is the cost function we have considered, and its derivative or gradient is this one. Derivative is, I'll call it g. This is your 8w minus 12, and initial guess in the starting point is wi, that we need to mention, and then in a loop we'll compute the gradient each time. So gi would be at ith iteration, it would be g of I would be 8 times of w of I minus 12, because this is the gradient at iteration I. Suppose w of I is the current weight. Okay, that time gradient value will be this one. And once we obtain the gradient value, we can modify our position. Okay, wi will be modified to wi minus gradient. Okay, with some step size modification mu into g of I. That is your w of I plus 1. Right. So this is the code only. Now I'll show you simulation result. First, I'll consider the step size 0.02, and initial guess is minus 5. This is our initial position. And here you will see the function. So you see here this cost function, right? And now you can consider here, this is the cost function, j equals to 4w square minus 12w plus 13, and initial value is this one, w equals to minus 5, and you see this is your minus 5, right? And that time this is the cost value, and step size we have considered as 2 into 10 to the power minus 2 means 0.02, right? So at that point we want to find out the gradient first. So here what would be the gradient? That gradient, then we'll update those things. So we'll show you. Okay. Now you see. So this one at w equals to wn equals to minus 5, the gradient value is becoming 8 into wn minus 12. So if you compute this one, you will get minus 52. Is it right? And then we can go for the update. The update will be wn equals to wn minus b into g. And if you compute in this one, if you replace this g by minus 52, then you will get minus 3.96. It could be like this. So this is the next point. Okay, so we can come from this minus 5 to minus 3.96 in the first step. right? Now, so you see at that point, we'll get again this one. This is the cost, this cost value. And the second iteration, you will see this one. This is your gradient. Gradient value minus 4.3 10 to the power 4 means minus 43. This is then this one. And you see every time the point is moving towards this optimum point, and this optimum point is here, that you understand that it is 1.5 and it is coming closer to. So you see at iteration number 10, 11, it is approaching to this one. It is now towards positive side. It is more than 1 right now. So at iteration number 18, 19, and till 20, you see it is very close to this one, but it is not, it will attain 1.5. It is at 1.3. Okay, still you need to go to right side. So 20 iteration is not sufficient for that. So here I have shown these two plot. This side is iteration versus cost function, how cost value is reducing gradually. Okay, so you can see this one. Okay, right. So this is for the step size 0.02. You see this, it is too small. It is taking too much step to reach to this optimal point for this simple problem. So it is reducing gradually. Now we'll increase. Okay, we'll consider one more case. Okay, so initial value is, suppose if it is positive side, W1 is 6, then also you will find very similar, but only thing is that it will start from right side. Okay, you see. So that is our initial case. It is at 6. So this is the cost, and the cost value is again positive, this much. And then you can take the gradient here. Gradient value is 36. And if you compute this one, so this is this one. So obviously this point will be here. Next one is here. So you can follow these steps. It is shown very clearly. Okay, all the steps are shown clearly how it is. So you see one thing. So when it is far away, it is taking larger steps. When it is coming closer to the optimum point, it is taking smaller steps, because gradient value is reducing. You see, gradient value is reducing gradually. So it is moving towards the optimum point 1.5 gradually. Right? So this is, so at 20 iteration, its value is 1.637565. So that is, here also it will not attain the optimal point 1.5. More iterations it has to go, then only it will reach to this optimum point. Fine. So we need to increase the step size. We should check how convergence rate is improved. So we'll consider same initial size, initial point minus 5. So here you will see so this is the starting point minus 5, and now consider this step size, it is 0.09. So you see from here it will come to directly here, this thing, next here, next here. It's very fast. In the first step is too large, then steps are a little bit slow. Okay, So after fifth iteration only it is moving to 1.99499 like that. So it will attain this optimal point very quickly. Okay, so by 10th iteration it will attain completely. So you see how quickly this cost function is reducing. In the first step only it is reduced from this value to, I think it is around 170 kind of thing, and here it is less than 20. Okay, then in step 3, step 2, it come here, then gradually it is reducing. Okay, so it's very fast. Now if we increase it further, will I get better convergence rate again? So I'll consider mu equal to 0.2. Now see for this one what is happening. So here consider the step size 0.2 only. Okay, this is the important thing. The gradient is same. So as step size value is large, its value is becoming very large. So it is crossing this optimal point. You're going right side to this one. So this is the next step. Then again, next one is coming here. And again, it will coming here. So you see, there's a zigzag path it is following. But still it is good. It is converging. It is converging to this optimal point very quickly. Okay, but path is different. Earlier it was smooth path in one direction only. Gradually it is coming down. But here you are finding some zigzag path. Okay, so here this one could be called as overshoot undershoot kind of thing, right? So here also you will see this cost function is reducing sharply. It's fine. Now we'll increase it further, mu equal to 0.24. Then what will happen? So here you see the step size value is 0.24. So if I consider this one, obviously it should go right side, but too far away. So it is reduced little bit only cost function. So here also you will find zigzag path, but this time it is reducing gradually again. Cost function is not reducing drastically. The zigzag path. Okay, but still it is converging, right? So this is the cost value, how it is reducing. So you see it slowly it is reducing. Okay, in 11 iteration it is coming down to minus 40 only. So you see the minimum cost value is its value is 4 only, but still it will attain close to 40. So we'll increase the step size further. We'll consider mu equal to 0.26. So you see in this case what is happening. Okay, so you see the first step it is coming to 8.5 means here. Now you see the cost value is more. Again left side cost value is further more. The cost value is increasing. It implies that the algorithm is now diverging. The points are moving away from this optimal point 1.5. So you see the points, these are the points. Okay, minus 10, minus 14, plus 14. Okay, all those things. And from this figure it is very clear that the cost value is increasing, means algorithm is diverging, right? So here we have shown all the plots. So you see mu equal to 0.02, this is the convergence rate. And if you increase a little bit more, so 0.09, it is too good for this algorithm. This step size is very good, converging very fast, green one. Then if you increase it further, 0.02, so its convergence rate is not increased. And we have shown that that time we'll have some zigzag path, but still okay, it is converging. But 0.24, this convergence is very slow, and again zigzag path. So these two are not desirable. We want to get a best optimal mu. So how to find this optimal mu, that will be discussed in next lectures. But here I'll show you. First I'll give you the conclusion for this video. The gradient descent, so I've said that gradient descent algorithm is very simple, but it is most effective for convex optimization problems. Okay. And for one-dimensional problem, we have shown that how gradient descent algorithm is converging, and we have got the concept. And for this one, simply you can write Wn plus 1 equal to Wn minus mu into Gn. You see all are scalar quantity, only one quantity, one variable W, and G is also one variable. That G means gradient of this cost we can compute, and we can put mu Wn minus mu into G of n, where J is the cost function and mu is the step size. That's simple. So in upcoming videos, I'll be taking one example from adaptive signal processing. So in particular, I'll show that if I consider one tap filter W, okay, that is unknown coefficient. This is the input sequence xn, and a white noise is added, and then we will get dn. So in this case, dn and xn, these two are only available, and we assume that vn is zero mean white sequence. So from this input data, this one xn and dn, and finite number of data, we'll try to estimate this w. And we'll show you this, that of this updated one, w cap, will give you suppose d cap, right? And we'll define the proper cost function for this one, and we'll show how to calculate the gradient and how to use gradient descent algorithm for this one in detail, step by step. And I can show you one simulation result, what we are going to show in the next simulation. You see, it will be interesting. First we will get the data, the x data and y data, or d data, okay, and those will be plotting, scatter plot we will having, and we will try to get one relation, this d equal to x into w. So it's a linear one, so I want to get a linear equations passing through origin that will fit those lines, and you see how iteratively it is fitting these lines. I'll show all the things in step by step. You see, errors are converging slowly. Okay. So this problem will be discussed in detail. I hope you will enjoy these things. And then we'll also develop the gradient descent algorithm for a higher dimensional problem in the next video. And then we'll take one problem from that one NRT function we'll discuss in the two-dimensional problem, and there I'll show you that how algorithm is converged in two-dimensional. Okay, so the contour plot will be introduced. For the meaning of contour plots, so that concept already I have given in my previous lectures, you can go through that one. So here I will draw the contour plots for my one cost function. So this is the cost function j, two-dimensional w0, w1. So these are the contour plots, and this is the cost function, right? And in the below you see this cost function, we have also drawn the contours. And then we'll show if this is our starting point at this point minus 2,4. Okay, from here onward, what will be the next step? You see, the next step will be here. And you see, this is the optimal point. This one will be the optimal point. So you see, it is coming gradual. Okay, and this direction will be conjugate gradient. I'll be discussing this one. So in conjugate gradient, it will take only 2 steps to reach this optimal point for 2-dimensional. So conjugate gradient descent algorithm is excellent one. So it's very fast. I'll be discussing that algorithm in detail. Okay. So keep watching. And if you have not subscribed yet, you can subscribe to this channel to get more videos. I hope you'll enjoy those videos.